All right, welcome. We're going to go through antiderivatives today. And so this is going to be part two of our calculus preview. The first one was on derivatives. So as you can see by the name, antiderivatives are going to undo a derivative, meaning if you take a derivative and you get some function that we could call a slope function, meaning it's a function for how the slope changes, then if we do an antiderivative, we would go back to the original function. It undoes a derivative. In doing this, what we're actually doing is we are doing the area under a curve. And so the key theme here is it's the area that's accumulated as we move along the x-axis and trace out more shading area under the curve. So for example, if we go from 0 to 10 here, and we have a linear graph described by the function y equals 0.5x, this triangular area would get bigger and bigger and bigger. The area accumulated as a function of x, then, we could actually figure out by doing what we call an antiderivative. You might be wondering, where did this come from? This area accumulated equals 0.25x squared. That's the goal of this video, is to figure out how do we give x as a, y as a function of x, and then figure out how much area is under that curve as a function of x as well. This would be easy if it were a triangle. We actually could just do 1/2 base times height. Similarly, if we had a straight line that's flat, we could do rectangular area. Where it gets trickier is if you have something like this, where you have this curving or nonlinear graph. In this case, it's a quadratic, described by y equals 0.05x squared. And again, we can see that there's this area accumulated, described by the function 0.17x cubed. And again, it's like, where is that area accumulated function coming from? It's coming from the antiderivative of our original quadratic up here. So that's the conceptual basis for what we're trying to do, is get the area under a curve. If we jump over to Desmos, you can see here, this is that same quadratic. And if we allow ourselves to shade here, if I were to let then x increase, the amount of area is going to change quite a bit, right, as we get farther and farther, right? Because you can see that it's going to get increased by a bigger and bigger and bigger amount. We can also do intervals where it's like, what if I just wanted from 5 to 10 instead, right? Then I could go from 5 to 10. So these are the things we're going to try and describe, is area under the curve, and we're going to try and do so by creating a function that we can use. We're starting with the word antiderivative because it implies that we're doing the opposite of a derivative or undoing the derivative. But moving forward, we're probably going to use integral as the term for this. They're pretty much synonymous. There are some minor differences that math will explain. But for our purposes, we can use them interchangeably, integral and antiderivative. So how do you talk without sounding awkward? Well, first of all, we're probably going to use the word integral, but we could use either one. So we're going to be integrating a function, or taking the antiderivative, is finding the antiderivative. Those kinds of things would be how we describe it. So determining the area accumulated function, we're going to refer to as integrating some function, and that will then give us the area accumulated function. This is the same thing as saying, let's take the antiderivative. We're going to use that power rule. The power rule is the same thing that we had when we did derivatives, but the opposite, because we're doing antiderivatives, which we are again going to be calling integrals. This is going to be useful for any kind of polynomial that we would be using when you get into more advanced functions and composite functions and all kinds of different things. Then you're going to have a bunch of different rules and techniques for how to both differentiate, meaning take a derivative, and to integrate, meaning do the integral. In Calculus AB, this will be at the end of January. In Calc BC, this is actually going to be towards the end of semester 1 that you're going to be doing power rule as you encounter calculus. So given any function, I'm just going to give some random looking one here. Y is equal to some constant a times x to the n power. Given this, if we want to get the area that accumulates as a function of x, then we need to do the antiderivative, or we need to integrate this. And so this is, if you notice, this is actually the opposite of what we would do with a derivative. And so we would just take whatever the power is. If it's squared, we would make it 3 by adding 1. If it was cubed, we'd make it 4 by adding 1. And then whatever power we end up with when we add 1, we're going to also put that down in the denominator dividing by it. So one of the pro tips here that I would say as you're getting used to this, if you do an antiderivative and get a function, then you could actually just take the derivative of that and see if you get back to where you started with the original function. That's a great check that you have to use. Same thing likewise with if you find the derivative of a function, then you can check your work by taking the antiderivative and see if you can get back to that original function. In terms of how we write this, we can start with slopes and derivatives. The idea would be if we had a delta y over delta x, your rise over run, that was how we got the average rate of change, and this would assume a constant or average slope value. For example, you could get the change in y-axis, that would be the range over the change in x-axis, the domain, and that would give you the slope of a secant line between just 2 points on a line. If we're going to be doing the instantaneous slope, then we're going to shrink down that delta x into a tiny, tiny, tiny little change, and that will essentially give us the slope of a tangent line. So it's the instantaneous rate of change would be the slope of a tangent line. And so that's what a derivative is doing. It's going to be tracking how does that slope value, which can change then, right, as it gets steeper or less steep, how is that changing as a function of whatever's on your x-axis? The way we did that was by taking our random function here, a times x to the n power, and we were then subtracting a power, but multiplying by the original power that we were starting with. Over here you can see that we're actually undoing that over here, right, by adding a power and then dividing by that new power. So they will be able to go back and forth or undo each other. With integrals or antiderivatives, what we're trying to do is area. So that's going to be your base times height. So we would have your average height, meaning if you were having a change, like a triangular, linear graph, I should say, and you had a triangular area, then we would be finding the average y value times the change in x. That would give you a base times height calculation. And this would be useful if you had a constant rate of accumulation of area. The way we write this is a little wonky, and calculus is going to explain this much better. But what we're going to do is take the integral, which is this integral sign, looks like an S, which makes sense because you're going to be summing a bunch of little dx's and the y values. We're going to get into all that in calculus. For right now, you can just think of this as a notation thing. So you'd be doing integral sign, the function that you're integrating y, with respect to x. This is useful if there's a changing rate of accumulation, meaning if we have a function that describes how it's changing, meaning nonlinear in particular. So again, if we have some random function here, we would then do the antiderivative or integral using this method, but really we're focusing in on this left side, which is going to be the notation for saying I'm going to be taking an integral or I'm going to be doing an antiderivative here of function y. Let's see if we can look at an example here and see the pattern. So if we start with some function y that's written as a function of x, like this polynomial here, this quadratic, which is graphed, if I do the derivative of this, then it would be taking the slope for this function and plotting that now as a y-axis value, and this would be the slope graph. We in calculus can call this the derivative graph. Its function we could find by just simply doing our power rule for derivatives, right? So that 2 comes out in front, so we have 2 times 3 is 6, and then we subtract a power, leaving just x to the first power. That's where you get the 6x. In this term, the x is raised to the first power, so 1 comes out in front, and when we subtract 1, it's x to the 0 power, which is 1, so we simply are 2 as a constant, and then 12 would be 0 because there is no x there. So it would be x to the 0 power would be essentially what we could imagine right here, and x to the 0 power when we bring 0 out in front will give us 0. So now that we have our derivatives graph, our slope graph, and slope function, then I could actually go back to the original graph by integrating. And so now if we were to do the same thing, but integrate, right, start here. So 6x, we're going to add a power, so it's going to make it x squared, and then we're going to divide by that power, which is 2, and that's going to be then 6 over 2 x squared. That gives us our 3x squared, and we could do the same thing for the rest of the terms, and that allows us to go back. In fact, let's take a look at this linear graph here that represents the rate of change being plotted on the y-axis. Let's go back to Desmos here. This is that same function, 6x plus 2. And as this area gets a wider and wider base, you're going to see that it's going to be more and more and more area, but it's not going to increase the area evenly. It's going to get much more area as it gets farther along the x-axis. So that's going to create an uneven accumulation of area as we get a bigger and bigger x. An example of this, don't want to traumatize anybody here, but let's say we were going to get some snow, right? Then we'd be looking at snow accumulating, right, at a rate of some amount of inches per hour. So each of these bar graphs is 1 hour, and so you can see the amount that's going to be coming down per hour, right? But that's not telling us how much snow we've accumulated. That's just telling us the rate that snow is falling. So we can see it's going to be bad driving between 7 and approximately 1 p.m. here, as it's coming down at a high rate of inches per hour. Okay, now what's going on with the accumulation? Well, if we were to plot this rate, right, and integrate it, then we would be able to add up the total area that we have as it moves. Now notice here in this rough hour here, a rough segment here where it's from 7 to about 1 p.m., that's when it was coming down a lot. So see how it's quickly gaining area as opposed to when it is not really gaining area for those first 2 hours. You can see that we didn't really gain too much accumulation at that point. So it's important that we go between the idea of rate of change and the amount of accumulation we have. Now revisiting our graph that we had, as we show the area, right, was getting bigger and bigger. And when I say getting bigger, I mean it's getting bigger exponentially, right? Because it's not an even amount of area that it's adding. The area underneath this is going to get much and much bigger as you get farther down the x-axis. So that creates this nonlinear accumulation that you can see. If these were flat lines, a constant rate, then you would have a linear graph over here, and the antiderivative would support that. So let's take a look at a few examples of integrals here. So if we're given that same function that we had on the first page, where y equals 0.05 x squared, to figure out the function of its area accumulation, we integrate that function, and so it's going to be 0.05 x. We're going to add a power, so from 2 we're going to add 1, that will give us 3, and then we're going to divide by 3. And that creates our area function. This is a velocity time graph. So, velocity as a function of time. So when we integrate this as a preview, or if we already know this, this is going to give us delta x. We know this because the area of a velocity time graph gives us delta x. So integrating a velocity time function gives us delta x. When we integrate this, it's the same thing we've done here a couple times now. We're going to have 10 times t, we're going to add a power, and then divide by that same power. We're going to divide by that number, the integer. And 4 by itself is the same thing as 4 times t to the 0 power, because t to the 0 is 1. So we're just going to add 1 integer power there, and then divide by what we end up with. And then simplified, that gives us 5t squared plus 4t. It would make sense that if we have the rate of change changing linearly, that then the accumulation would be this quadratic. It would be getting bigger and bigger in a nonlinear way. This is a force as a function of time. This is going to give us impulse when we do area, as we'll learn in Unit 4. And when I integrate this, it's just going to be negative 5t squared, and that's going to be add 1 power, that's 3. We're going to divide by that 3, and then plus 2t, and then we're going to add a power to get 2 and divide by 2. And simplified, we get this expression here. And so you can see it's with polynomials, it's going to be using power rule, and it's no problem. And then as we learn more and more calculus, you can do more and more functions.